Okay, so welcome back to the second part of this sixth lecture. And at the end of Monday's lecture, I proved the so-called second representation theorem of Kato, which was looking at all the things that we had done before about fractional powers. This was no longer complicated. And nevertheless, it's a very remarkable result that tells us whenever you have an operator that comes from a really nice form, so this form has all the nice properties that we had in chapter 2, bounded, accretive, elliptic, symmetric. But if you have an operator that comes from such a form, the form and the square root of the operator, so the operator to the power 1/2, are very intimately linked. And this square root represents the form in the sense that you can rewrite the form as, using the square root, you can rewrite the form by using the scalar product in H. So this is the scalar product in H here. And that this thing is really remarkable. We can shed a little bit of light to this, but when we look at the special case where L is an elliptic differential operator, so a divergence form operator as we had them in lecture 3. So this is the so-called Kato property. As you see, the name Kato is very present here. It will come more often in the next minutes. So the Kato property for for self-adjoint operators. Here we have a self-adjoint operator, self-adjoint elliptic operators. So we look at the case where L is a divergence form operator of second order with elliptic coefficients, minus divergence A gradient, elliptic operator, which means that the coefficients are elliptic, in divergence form with Dirichlet boundary conditions. So we look at this operator on L2 with form domain H10 with Dirichlet boundary conditions. And to get in this context of the second Kato representation theorem, we need the coefficients to be Hermitian, because if they are Hermitian, then this form is symmetric, and then the operator gets self-adjoint. And we look at this on some open subset of Rn, and we need that A of x and A of x star is the same for almost every x in omega. So we need Hermitian matrices as coefficients. But then we know from our lectures that this operator comes from a form. This form is accretive, bounded, elliptic, symmetric. So this theorem applies, and it tells us that the domain of the square root of L is the same as the form domain, so the space V, so this is H10 of omega. And we will see there is even comparability of the norms. So the norm of square root of L applied to U in L2 is equivalent to the norm of U in to the norm of gradient of U in L2. This immediately gives you equality of the norm here, equality of, not equality, comparability of the norms here, equivalence of the norms here. This is even a stronger statement than equivalence of norms here, because here the norm is the norm of U in L2 plus the norm of square root L U in L2, and here the norm is norm in U in L2 plus this term. And what this tells you is you even get comparability of the two parts of the norm that is not the same in both cases. Yeah? So this is even a stronger statement. And this is also the only statement we have to prove, because the rest is just Kato's second representation theorem, and this is true for all u in H10 for me. Okay, so one line of proof to get this equivalence here. We have to look at the norm of square root of L applied to u in L2. Then, okay, we know by the Kato theorem that this is the same as A of u. So if you put u equals v, this gives you the square of this norm. So this gives you A of u, so the quadratic form of A. Then you can use boundedness of the form. This gives you this constant capital lambda times the gradient of u measured in L2. This already gives you the first part of the equivalence of norms here. Now you use ellipticity of the form. This gives you capital lambda divided by small lambda, so this is number 327 times the real part of the quadratic form. This is ellipticity of the form. Now the form is symmetric, so the real part is the same as the form itself, and this is again by Kato the L2 norm squared of square root of L applied to u. So these two terms really are equivalent. And okay, now I said this is a remarkable result, and you can say why. Seems natural if L is a second order differential operator, then its square root should behave like a gradient. Oh, why is this remarkable? It is remarkable because when you look at the domain of L, of the whole operator L, this domain very much depends on the coefficients A. Think back of the exercises in lecture 3 where you constructed operators L in divergence form where the domain, the intersection of the domain of the operator and the CC infinity function was empty. The zero function. So the domain of L very much depends on the coefficients. And if you change the coefficients, the domain will change. And what this result now tells you, okay, the domain of L depends on the coefficients, but if you look at fractional powers and you look at the square root, this domain is always the same. This domain does not change with the coefficient. So somehow, if you increase your fractional power up to 1/2, the domains are always the same, and then after 1/2, at sometimes for different coefficients, these domains begin to be different. So there's something happening, something interesting. But up to the exponent 1/2, the domain does not see the coefficients. It does not see anything about the operator L. The domain is always just H10. The domain of the square root is always H10. And that's really a remarkable thing. We will see in later lectures, we will see more why these things of this sort of questions was of interest to Kato. But he dealt with these operators and with these square roots, and he posed if you see this result, a very natural question, which is then known as the Kato square root conjecture. And this Kato square root conjecture is the following. It's also this is Corollary 613, which is important because the Kato square root conjecture is 613 remains valid without the condition A of x star equals A of x almost everywhere. So without the coefficients to be Hermitian, without the self-adjointness of the operator. And yeah, Kato posed this. So Kato wanted to have this. Yeah? So what was Kato's question more in detail? And this dates back to 1961. So Kato asked this question and made this conjecture in 1961. And yeah, rephrased, his question was, does this, so that the domain is independent, the domain of the square root is just the same as the form domain. Does this remain valid? So he wasn't interested, because his background was a partial differential equation. Kato didn't, he was a great mathematician, but his focus was on partial differential equation. He was not doing abstract operator theory or something, or he did it, but always having in mind an application for some partial differential equations. And so, in fact, what he was interested in was small perturbations of the self-adjoint case. So, so you have this coefficient, and you have to you perturb it a little bit, and he wanted to be this property here to be stable under perturbation. So what does that mean? That does mean what he wanted is that if you have L0, so the unperturbed operator, and L1, the perturbed operator, he wanted that somehow he can estimate this difference by the difference of the coefficient matrices. So A0, A1, here denote the coefficient matrices of the operators L0, L1, times the gradient measured in L2. And for this to be true, and he wanted that for small perturbations, so if the difference between A0 and A1 in some sense is small. So in this sense. Okay, and what was known by, and that's why he made this conjecture, what was known at the time is that the answer is yes if you have star, so this property here, for all complex elliptic L infinity coefficients. And so he was led by his questions coming from PDEs, he was led to hoping or to trying to prove that he can get this result without the self-adjointness condition. And if you look back into the proof of the second representation theorem, you will see this hinges 100% on the self-adjointness condition. So you will not get this proof working. Because what you do at some point is you have the square root of L star, you put square root of L to the other side, you have a star and you say, okay, this is self-adjoint, so there is no star and everything is fine. But for the general case, you have a star here, and once you have a star here, you cannot conclude. Okay, and yeah, at that time, this looked just like an interesting question to be given to some PhD student and to work a little bit about it, and it got more and more complicated. And it really got complicated, but to take out the question, is it true or is it not true? It is true. The answer is yes, the Kato square root conjecture is true. So we can now call it Kato square root property and not Kato square root conjecture. And this was proved by 5 people: Pascal Aucher, Steve Hoffman, Aucher, Hoffman, Lacey, then the McIntosh and Chamichian. And it was not really a question to give to some PhD student, because this is 5 really, really big names in harmonic analysis. And it was proved in 2002. So it was 41 years. More or less, yes? You're right. This is me miswriting here in the infinity norm. This fits better here, yeah. Sure. And this was a really big breakthrough, appeared in Annals of Mathematics. And it's one of the greatest breakthroughs in this area in the last time. Pascal Aucher writes in some overview paper, which I find nice, that the Kato square root property is an interesting mathematical object because the question behind it came from PDE theory. So the question is a PDE theory question. It was formulated in the language of functional analysis. So the question itself is, if you have a nice operator coming from a nice form, is the domain of the square root of the operator the same as the domain of the form? Yeah? So this has nothing to do with PDE from first glance. It's formulated in a completely different field of mathematics. And then it was solved 40 years later using real harmonic analysis. So it was solved in the 3rd realm of mathematics. So it really puts together very, very different parts of analysis, and this also makes it a very interesting thing. On the way from 61 to 2002, and on the way in this quest to solve this problem, much interesting mathematics was born. In some sense, one could also say the functional calculus that we saw is a result of this quest to solve this problem. So the functional calculus was invented by McIntosh, and McIntosh did many things in his very rich mathematical career. But there was one constant thing about him. He always thought about Kato square root conjecture. And he first saw it in his early career, and he worked on it really until the end. And this was somehow the fixed point of his research, and also all these stuffs about functional calculus. He invented also always to tackle this problem. One of the aims of this lecture in the Internet Seminar is to develop the tools that are necessary to show you a proof of this conjecture in the case of Rn, and to show you what are these methods that were invented in this area to tackle this conjecture. So this is one of the aims that we had for, and it will be 5 more lectures from now, so 5 more weeks from now, just to show you the techniques and the methods that needed to be invented to prove this conjecture. And it's not in the sense that they were invented just to prove this conjecture and have no importance elsewhere. So this conjecture really advanced this whole topic of real harmonic analysis and produced many techniques that proved to be very, very powerful in several areas. And this is, so the idea here is to show you these techniques. And then we hope in the end to show you a proof of the Kato square root property. Okay. So this is to look forward. At the moment in this chapter we are still looking at, so the headline is first applications of the functional calculus. So we are looking at what we can do with this functional calculus. And I already said this one or two times. One of the philosophical points is that we want to use functional calculus as a replacement for the Fourier transform. So the Fourier transform helped us in section, what was it, 4 or something, to find things about the Laplace operator. So the Laplace operator we could treat by the Fourier transform, and we found many information. We could define a functional calculus for the Laplace operator using Fourier transform. And somehow we want to use the functional calculus to extend these results that we found for this special operator to the much larger class of elliptic operators on divergence form. So this is somehow the philosophy. And one of these instances I can show you now. The fifth part of this chapter is about the Calderon reproducing formula. And this is also something we already saw for the Laplace operator, and which we can now generalize to more general sectorial operator. So as a reminder, from chapter 4, this was 410, there we proved for the Laplace operator that if you have a Schwarz function, so the function in the Schwarz space, that is 0 at 0, and that is normalized in such a way that if you integrate f from 0 to infinity with respect to the measure ds over s, so our measure, that this is normalized to 1. And this is just a normalization. And if you have any Schwarz function that is 0 and 0, and which is not the 0 function, you can always multiply by f by some constant, and you get that one. Okay. And so what we proved in this 410 was that then you can write a function u in L2 in a more complicated way, introducing this function f. So you can write it as, by using functional calculus, you plug in the Laplace operator into the function f of minus tz and apply it to u, and then you integrate this function with respect to the measure dt over t. This was the result in 410. And now if you look at this result, it looks like it could be generalizable for us, because the proof was by Fourier transform. The proof was using that you can rewrite the Laplace operator as a multiplication operator by Fourier transform, and then working with the integrals, and everything worked out. But in the final result, the Fourier transform is no longer seen. There's no Fourier transform here. The only thing that you have is a functional calculus. So you have f of the operator. So at least we can write down, if you now take L instead of Laplace, we can write down a formula that looks similarly, and then we can try to prove it. And this is what we will do now. So we will replace the Laplace operator by some function L, by some sectorial operator L. And to do this, we also have to change a little bit the functions that we use here. That we used here, a Schwarz function is just reminiscent of the Fourier transform, because Schwarz functions fit very well to the Fourier transform. If we think of our functional calculus, of our holomorphic functional calculus, what we need here is holomorphic functions. So we will switch for the f from Schwarz to holomorphic on a sector. Okay, so before I can prove the corresponding reproducing formula for sectorial operators, I have to do some short lemma, which is dealing with this f of minus TL, that this thing has the right properties. So take some phi again bigger than the sectoriality angle of our sectorial operator. Take some function from the Dunford-Rees class. And then look at the following map that goes from 0 infinity to the bounded operators on H, and that sends T to the operator f of TL. This is exactly the map that we integrate here. Remember, this is for the operator minus Laplace. So L replaces minus Laplace, and so this is the function that we have to make sure that we can do integrals with it. So we first have to show that this is continuous, stuff like that. So this is the claim of this lemma, is that this function, I will call it capital S, is continuous and bounded. In particular, it's measurable, and we can do integrals and all this stuff. So this is preparation to being able to write down this integral. Okay. So why is this the case? F is in the Dunford-Rees class, so again we have to go through the three cases. F is a constant, or F is a one function. F is a resolvent, or the function 1 plus z to the minus 1. And then the third case is F being an H0 infinity function. The first one is again easy. So if F is the constant 1 function, then this map S maps T to the constant 1 function of TL, so to the identity. So this is constantly the identity on H. Yeah, this is bounded and continuous. No problem here. Second case, if F is the inverse of 1 plus Z, then I will even show it for general resolvents. Yeah? So we consider lambda minus Z to the minus 1 for lambda being outside of the sector with angle phi. And then you take lambda equals minus 1, and then you get it. Okay, so we have to look at this function. We have to plug in L into f of TL, f of TZ, this is this one. Okay, we know how resolvents act on L. This is nearly a resolvent, so just rewrite it as 1 over T minus Z to the minus 1 of L, and then you see this is 1 over T minus L to the minus 1, and this is 1 minus TL to the minus 1, so lambda. Okay, so the function acts as one would imagine. Okay, and now why is this bounded and continuous? It's continuous because it's even, this you see best here, for T positive, it's even holomorphic in T. Because the resolvent depends holomorphically on T, and 1 over T here for T strictly positive doesn't change this. So this is holomorphic in T, so in particular it's bounded. Particularly it's continuous. And it's bounded by sectoriality. So it's continuous because it's holomorphic. And it's bounded because the norm of S of T is the norm of this one, or better take this one, it's the norm of this one. Yeah? And this is T to the minus 1 times the norm of lambda t to the minus 1 minus L to the minus 1. Okay, and now our operator L is sectorial, so the resolvent, the norm of the resolvent goes like 1 over the resolvent parameter. So by sectoriality, this is less than t to the minus 1, 1 over lambda t to the minus 1, or shorter 1 over lambda, and this gives you a bound. Okay, so it's also bounded. Last thing that remains for this lemma is the case where f is a regularly decaying function. Okay. Then we want to look at f of TL. First note that z sent to f of tz, this is again a regularly decaying function. Yeah? If you just dilate the argument, this does not destroy holomorphy, it does not destroy boundedness, and it does not destroy having going to 0 at 0 and infinity. So this is still in the same class. So we can put in the L here. Okay, so f of TL, L of H. I will show boundedness is using the definition via path integrals. F is a regularly decaying function, so this is defined by a path integral using the usual path gamma psi. I will not write down again, but this is the path that goes along the boundary of a sector of angle psi with psi between phi L and phi. Okay, then you have f of tz, z minus L to the minus 1 dz. Okay, that's the definition of the operator f of TL. And now you use that this function decays polynomially at 0 and infinity, so there is some constant c such that so take the norm inside. This gives you an absolute value here. This you can estimate by some constant c times the minimum of t tau to the s and t tau to the minus s. And then there is the norm of this resolvent, but the norm of this resolvent goes like 1 over the parameter from the path, so this gives you 1 over t, 1 over tau. Okay, so this is the decay of the resolvent, this is the decay of the function f, and as usual the decay is as good that this is a nicely absolutely convergent integral, because you have enough decay in 0 and enough decay at infinity. Okay. But we want to show that this is bounded in t, so there is still some t left, but this t here only looks like it would be important, because what you can now do is just you do a substitution. Rho is equal to t tau. This gives you c over 2 pi. Integral stays between 0 and infinity. This gives you a minimum of rho to the s, rho to the minus s, and then this is half measure, so doing a substitution like that will not change the measure, so this is d tau over tau. And now you see this is independent of t. In fact, it's independent of t, it just looks like depending on t. So this is bounded independently of t. And what then remains to do is to show that this is continuous in t, and this you can do just by also rewriting the operator here by the path integral formula, and then you have to have a limit t going to t0 that you have to get inside the integral, and this can be done by dominated convergence. So you have to find the right measurand, but once you have this measurand, you can put in the integral, you get the f of t0z, and this is then continuous. Okay. One note in this context, we work here with the operator f of tl. And I have used the functional calculus for L, so I looked at the function f of tz and plugged in the L for the z. One might have a different idea to do this. The different idea would be to take the operator t times L, and then one shortly has to think about if L is a nice sectorial operator, does the same hold for TL? But the answer is yes. So you can also plug the operator TL into the function f. But then you use a functional calculus of a different operator. It's not that much different. It's just 5 times the operator before, but it's a different operator. And I said when we introduced the functional calculus, always be aware that this is not like this is the variable and this is the function, but you have a fixed operator and you put it into different functions. That is what the functional calculus is about. So changing the operator is always something you have to be very, very careful with. And it's not completely obvious that these two ways to do it, so look at the function f of tz and plug in L, or looking at the function f and plugging in TL, should give rise to the same operator. It is true, the two calculus are compatible. That's a special case of something that is called composition rule for functional calculi, but this is not obvious. And that is why I somehow did it here in the puristic way to say, okay, we stick with our operator L, and we only work with the functional calculus for L. That's why I put it into this function. If you want to read more or know more about this composition rules for functional calculi, the right place to look is again Markus Haase's book on functional calculus, where he discusses this extensively. But I just wanted to make the point that this is something to be cautious. Always keep in mind that if you change the operator, you have a completely new functional calculus. Okay, so that as a side remark. And now I can write down the general version of the Calderon reproducing formula. And this Calderon reproducing formula also is a tool that we will use again and again in the upcoming lectures. So this is why it's a really central theorem for our course. We will use this will be used again and again. Okay. Calderon reproducing formula. And the situation is again, take some angle phi bigger than the sectoriality angle. And now, look back up there. What is the aim? The aim is to do this reminder, this formula that we had in the reminder for the Laplace operator for our sectorial operator L. So we want to have a formula of this form, and as I said, not for f being Schwarz, but for f being an h infinity 0 function. And so what we need is again such a normalizing condition. So take a function that is regularly decaying on the sector, and again normalize its integral against the Haar measure to 1. So we take a function that is normalized to integral 0 of infinity f of t dt over t is 1. Note by the decay of f, this is an absolutely convergent integral. So for every function f, there is some number that you get here. And if if this number is not 0, then you can always normalize it to 1. So whenever you have a h0 infinity function that has where this number is a non-zero value, then just multiply by the right constant, then you get 1. Okay. And then the claim is that for all u in the in the closure of the range of L, you get, again, a Calderon reproducing formula. So you get the formula that the integral from 0 to infinity f of t Lu integrated with respect to Haar measure, compare with the formula for the Laplace operator. For minus the Laplace operator, it's exactly the same thing. So this should be u, and it is u, at least for all u in the closure of the range of L. And this integral has, again, like in chapter 4, to be understood as an improper Riemann integral, or as an improper integral. So you have to understand this as a limit epsilon going to 0, you can limit r going to infinity. But these limits exist. Okay. And one additional thing, if you think back to our always used proposition 2.4, that we had the topological decomposition that the whole space H can be decomposed into the closure of the range plus the kernel. So if you have an injective operator, meaning the kernel is just 0, then this is all of H. So then you have the formula for all u in H. So if L is injective, then this formula here holds for all u in H. Again, the injective case is a little bit nicer. And that is why you didn't see this condition in the Calderon reproducing formula in chapter 4 for the Laplace operator, or minus Laplace operator, because minus Laplace operator is injective. So there you got it on the whole space. Okay. So now the big project is, let's prove this theorem. And so we do not have Fourier transform at our disposal. We have it, but it's of no use. So let's try to work with the functional calculus. That's why we developed this method to generalize things that could be done with the Fourier transform for the negative Laplace operator. Okay, so to start, just take some regularly decaying function and pick the right constants C and S positive, such that you have the usual estimate for this regularly decaying function, so that the absolute value of f of z can be bounded by the constant t times the minimum of the absolute value of z to the s and z to the minus s. So this is the usual estimate for H0 infinity functions, and this should hold for all z in our sector. Okay. And then we define some auxiliary functions. So take some numbers a and b, a greater 0, b greater a. So this is part of writing this. As I said, this is an improper integral. So we will look at the integral from a to b over the stuff, and then let a go to 0 and b to go to infinity. So take some numbers a and b, and consider the integral up there truncated at a and b. So consider the function capital F a b on the sector S phi to the complex number that to every z assigns the integral that we want to look at, but from a to b. So a to b, f of t, and now I have to do it with z, yes, f of tz dt over t. So it's not this integral in the operators, but it's the corresponding integral in the complex functions. And then later on we want to put in L. Okay. So we want to put in L. So the first thing you have to check is that this function fab is a holomorphic function. This can be seen in several ways. In some sense, it's a parameter integral. a parameter integral. You want to differentiate with respect to z, which is inside, so you have to look that you have the right measurement. You can do it by Morera's theorem. You can. There are several ways. They all lead to the same aim. This is a holomorphic function. So, for instance, you can do it by Morera. Okay, what I will want to look at is now, in a first step, we want to look at this function and find some properties of this function. And the most important property that we will look at is we want to look at the limit of what will this function do if we let a go to 0 and b go to infinity. That's the interesting stuff, because this is directly linked to this thing that we want to look at. And what should happen? What should happen if we look at this function, let a go to 0 and b to infinity? Then this operator, in some sense, should go to the identity. So what we want to prove is that this operator goes to the identity, or that this operator is the identity on U, at least on the closure of the range. It should be the identity. So what we hope is that this function goes to the function constantly 1. Because the function constantly 1 in the functional calculus gives you the identity. And this we will prove in this first step. So take a and b as both positive and b greater than a. And then let's check what happens. So what I want to prove is that this is bounded, that this is a bounded family of functions in H0 infinity. Okay, so let's look at this absolute value. Okay, we plug in the definition, put in the absolute value inside the integral. This gives you f of tz modulus dt over t. Okay, then we can apply our estimate here. So this is less or equal some constant c times integral from a to b, the minimum of t multiplied with modulus of z to the s, and t multiplied with modulus of z to the minus s, dt over t. So as soon as you have achieved this, this gives you already that fab is again a regularly decaying function. Why? So look at what happens if you let z go to 0 or z go to infinity. Then this minimum will tend to 0, polynomially bounded. This is on a bounded interval, so finding a L1 majorant to make the limit go under the integral is not the problem. So this will give you a decay, a polynomial decay in 0 and a polynomial decay in infinity. Okay, so that's the first thing. Okay, and second thing, again, do the same substitution, change of variables like here. Then one sees this, in fact, does not depend on the modulus of z. So set tau equals t times modulus of z. And then you find this is the same as constant times integral from not a to b, but yeah, it's some, what is it? If t is a, then this is a times modulus of z to b times modulus of z. Minimum of tau to the s, tau to the minus s, d. And again, it's again Haar measure, so this is d tau over tau. But now just estimate this by the integral from 0 to infinity of this minimum tau to the s, tau to the minus s, d tau over tau. This is finite. So this is a set of bounded functions. So these functions fab form a bounded set of functions in H0 infinity. So this is what we take from here. So this family FAB for 0 less than A less than B is a bounded family in H0 infinity. Okay. And now what we want to look at is the integral from 0 to infinity f of tz dt over t. So this is the limit a going to 0, b going to infinity of our functions fab. So this is the limit a going to 0, b going to infinity fab of z. And we can now conclude that this exists because for every this exists on every compact subset of S phi. No, it exists. Yeah, you can do this limit. So if you restrict yourself to a compact subset of S phi, then this is a bounded function on a compact subset. So you can take just this constant as a measure for the dominated convergence theorem and get the limit inside. And this is possible for every compact subset of the sector. So in a pointwise sense, you get it on the whole sector, and you get a uniform convergence on compact subsets of the sector. Okay, and this is a nice sort of convergence because that gives us that the limit function capital F is not only just a limit function, but it's again a holomorphic function. It's again a holomorphic function because it's a local uniform limit of holomorphic functions. And if you have holomorphic functions and you do locally uniform limits, you get again holomorphic functions. Okay, so this F is a holomorphic function in S phi. Then let's calculate what this F does on the real line. On the real line, f of z is what is the integral from 0 to infinity f of tz dt over t. It's the limit a going to 0, b going to infinity. But this limit exists, so it's this value, and we know this value because we fixed it in the beginning. It's 1. So on the real line, tz there's one thing missing, so there is still this z, but you can again do the same trick, change of variables, putting tau equals to tz gives you f of tau, and the Haar measure doesn't change, d tau over tau, and this is 1. This is what we imposed here. This is our normalization. And this does not depend on z. The dependence on z disappears here when you do this change of variables, which just shows that the function is constant. It's constant on the positive real line, and it's holomorphic on the sector. Okay, so this is a nice instance to use the identity theorem for holomorphic functions. So it's not only one on the axis, it's one everywhere, because the axis has an accumulation point in the sector. So this means that you get f of z equal to 1 throughout the sector. And that was what we hoped to find. Because in the end, this should be f of L, capital F of L, u, and this is u. That's the idea behind this calculation. Okay, there are 3 more steps to go, but I think it's good to take a little rest, make a short break, and then we will be back in 10 minutes. Okay, let's start again with the remaining 3 steps of the proof of the Calderon reproducing formula. We introduced our functions FAB, where we only integrate from a to b, and then we saw if we do the limit a to 0, b to infinity, the function that emerges is in fact the constant 1 function, so this looks nice. This was all calculations on the level of complex functions, so no operator involved. So the next thing to do is put in the L. So this is we first do for the functions FAB. So step 2 is what is FAB of L? It's defined, that is clear because we've seen FAB is a regularly decaying holomorphic function, so we can put in the L. But what is the result? And we will see it's what you would expect. It's just this one where the Z is replaced by L. But this we have to show. So take some psi greater than the sectoriality angle less than pi. Then just by definition, what is FAB of L? You can write it as a path integral, 1 over 2 pi I integral along the path gamma psi. FAB of Z, Z minus L to the minus 1 dz. This is just the definition of the operator of the functional calculus. And now put in the definition of FAB and interchange the integrals. So FAB is an integral. We interchange the integral. This gives you 1 over 2 pi I integral from a to b, integral over gamma psi. And then there is f of tz, z minus L to the minus 1 dz dt over t. And now you see the inner integral together with the 2 pi I here gives you again a path integral for the functional calculus for the function f of t dot, f of tz. So this is nothing else than integral from a to b, f of tl dt over t. So it behaves like it should. If you put in the L here, you get the L here. Okay, now we can start to do the limit. So this is step 3. We want to show that for all u in the closure of the range, these operators converge to the identity. Oh, no, there's a u missing here. So these operators applied to u converge to u. And we will do this in 2 steps. We will first do it on a smaller space that, however, is dense in this one. So we will do it on a nicer space where we can do this calculation easily, and then enlarge the class of admissible u by a density argument. So the first thing we will do convergence on the domain of L intersected with the range of L. This is clearly contained in the closure of the range of L. But it's a nicer space, and the nice thing in this space is we can now apply L to our u. Here this is not for general u in the closure of the range, you do not know. Okay, so take some u in this space, in the domain of L intersected with the range of L, and then use a nice function that we've already seen 1 or 2 times, z divided by 1 plus z squared. And Why is this function interesting here? Note, we do not take this as a regularizer because, first thing, we do not need a regularizer because all our functions are already in H0 infinity. And secondly, we do not know if our operator L is injective, so it wouldn't even be admissible as a regularizer. But we use it because also in the second lecture in our all-purpose proposition 2.4, exactly in 2.4e, we showed that our space domain of L intersected with range of L is intimately linked to this function. It's the same as the range of L times n1 plus L to the minus 1. So this was proposition 2.4e. So if you plug in L here, you get this operator. And the range of this operator exactly is domain of L intersected with range of L. This is 2.4e. And this we will use now. Because what does that tell us? That tells us if our U in this set is in this range, so we can take some V in H such that our U is E of L applied to V. So I plug in L here, apply this to V, and I get U because U is in the range of this operator. Okay. And we will use this V. So what do we have to calculate? We have to calculate the integral from a to b f of t L u dt over t. And we have to show that this goes to u for a going to 0 and b going to infinity. Okay. So this is, by definition, FAB of L applied to u. So now by step 2, we've calculated what that is. Now use this one. So this is FAB of L applied to E of L V. Okay, both functions are H0 infinity functions, so by the elementary functional calculus, this is FABE of L applied to V. And now this can be written, so this is a product of two regularly decaying functions, so the functional calculus is defined by the usual path integral. So rewrite that as a path integral. This gives you 1 over 2 pi I times the integral over FAB of Z, E of Z, Z minus L to the minus 1 dz. The V is missing. So, and now your question might be, why does he introduce this E? Why doesn't he do this calculation now without the E? What is the aim? We want to do the limit a going to 0, b going to infinity. We know what happens for this function. If you do the limit a going to 0, b going to infinity with this function, this goes to constant 1. Okay, and that's what we want. We want constant 1. We want the functional calculus for the constant 1 function, and then everything is good. Yeah, but for the constant 1 function, the functional calculus is not defined by path integrals. And it wouldn't make sense to do it by path integrals because this doesn't give you a convergent integral. You cannot do, if you do not have the E here, you cannot do the limit a to 0 and b to infinity, going that to 1 because you do not have you do not have enough decay. And the point of inserting the E is to get a little bit more additional decay to make this integral converge even in the limit. Because now we can do it. We know this goes to 1 pointwise. The E here gives us a decay of like Z in 0 and a decay like Z of like 1 over Z at infinity. So this gives, together with the sectoriality, this gives a nice integrable integral. And this gives you also the right Lebesgue majorant. So the point of the E is that it gives you additional decay. Okay, so that here you can now do the limit. A going to 0, 0 is 0, and b going to infinity. And what do you get? Okay, this goes to 1. This gives you 1 over 2 pi I integral gamma psi E of z, z minus L to the minus 1 v dz. So, and this is now just the path integral that defines the functional calculus operator E of L. So this is just E of LV. Yeah, but E of LV is U. So we are fine. Yeah, so, and now you see why we need this additional regularity of U, because this additional regularity of U allows us to write U as E to the LV, E of LV. This gives us the additional decay for the integral to get E of LV, so U. Yeah? So for all U in this set, we now have that these integrals converge to U. Okay, so on this set it's okay. So what remains is to enlarge the class of functions U where this works. So to get this equality for more functions. So this is step 4. Convergence on the closure of the range. And now it's just a density argument. And what we use is something we've already encountered in proposition 2.4. General thing, if you have a sequence of operators, bounded operators, and this sequence is bounded such that for some subset of H you get TGU goes to 0 for all U in U. It must be a bounded set of operators and it must converge on some subset of U. Then this convergence holds even on the closure of U. So then you can extend to the closure, and this is nothing more than a 2 epsilon or 3 epsilon argument, depends on how you write it down. It's just using the boundedness of the operators and smuggling in the right thing. In the lecture notes in chapter 2 it was written as a footnote. Please convince yourself that. Now I hope you convinced yourself. It's the same thing. Okay, and we will use this. So what does that mean? What do we have to prove? Again, looking into proposition 2.4. This time it's proposition 2.4e. There we saw that the range of L, the closure of the range of L, is the same as the closure of range of L intersected with domain of L. So, in fact, this set that we had here is dense in the closure of the range of L. So we can take this set, dom of L intersected range of L of U here. And then the only thing that we have, and we know that on U the convergence is fine. This is step 3. So what we only have to check is that our operators FAB form a bounded set of operators. Once we have that, the rest is this general thing, this 2 epsilon argument. So what we have to show so what is the work? The work is to show that this set of operators FAB that we want to do the convergence of, that this is a bounded set of operators in the bounded set of operators on H. Okay, and this is a little bit more work to do. In order to do this, it helps to decompose this FAB into 2 parts. And we will do this in the following way. So this FAB of Z, this is now again a calculation on the level of the holomorphic functions, but we know how to put in the L into this calculation. So we can do the calculation on holomorphic functions and then put in the L afterwards. This function, by definition of FAB, this the integral over f of tz with respect to Haar measure. And I will, as I said, we will decompose this into two parts. We can be written as an integral from 0 to b f of tz dt over t minus the corresponding integral from 0 to a. And now what I can do is I can somehow take the a and b out of the limits of the integral and into the functions. I'll do a change of variables, making this an integral from 0 to 1, so t going to t over b. So this is integral from 0 to 1 f of t bz. And what the nice thing is, again, we have Haar measures, so if you do a change of variable by just multiplying the variable with the constant, this cancels out. So this is dt over t, minus doing the same thing here, integral from 0 to 1 f t a z dt over t. Okay, and I will write shorthand for this. This is g of bz minus g of az, where g of z is defined as integral from 0 to 1 f t z dt over t. So somehow I put in the a and the b in the argument instead of the limit of the integral. And now we want to look at this function g, and we want to show that for this function g everything works fine, and then if you know that g of tz gives a bounded family of operators, g of tl gives a bounded family of operators, then you have here g of bl minus g of al. This is then also a bounded set of operators. So we have to prove it for g. Okay, so what happens? First thing we prove what I will prove is that this function g is in the Dunford-Rees class. So what I have to prove, this is some exercise in chapter 5 lecture notes. Being in the Dunford-Rees class, a sufficient condition for being in the Dunford-Rees class is having polynomial limits in 0 and infinity. So we will check this. So what happens for g? So I will look at what happens for small and for large z with g, and we have to show that there are polynomial limits in 0 and infinity. And the polynomial limit in 0 will be 0, so I look at the absolute value of g. I take in the limit inside the integral, and the absolute value inside the integral, and then I can estimate this function by tz to the s, times some constant. I want to look at small z, so I take this. So the estimate for small z, so this is less or equals z times the integral from 0 to 1 tz to the s dt over t. So, and now this you can just calculate. So this is constant times modulus of z to the, there is modulus missing, t modulus z. This constant modulus of z to the s, and there's remaining 0 to 1 t to the s minus 1 dt. This you can just calculate, and this gives you constant over s z to the modulus of z to the s, and you see this is a for z going to 0, this goes to 0 polynomially, so you have a polynomial limit 0 at 0. And analogously, you do it for large z, and this gives you that here the right limit is 1. And by the first step, you can rewrite this 1. So this is integral from 1. So using the first step, this is integral from 0 to 1 f of tz dt over t. This is definition of g of z. And the 1 you can rewrite as 0 to infinity f of tz dt over t. That was the first step, that these functions go for a going to 0, b going to infinity, go to 1. And now you see this is integral from 1 to infinity f of tz dt over t. And then you do the same thing. You estimate your f by the polynomial decay at infinity. You calculate the integrals. And what remains is z over s modulus of z to the minus s. So you have a polynomial limit at infinity, and this polynomial limit is 1. Okay, but what is important is you have polynomial limit in 0 and infinity, and the exercise 5.3 then tells you that this function is in the Dunford-Rees class. And that means, and this is 614, it's the lemma that we did in the beginning of this section that told us what if you start with a function in Dunford-Rees class, then the operators that you get, so then the operators that you get, if you look at g of TL for t in 0 infinity, this is the image of the map S that we had in the lemma 614. There was this map S that applies to L assigns the operator f of TL, so g of TL, and we saw that this map is continuous and bounded. So this is a bounded set of operators in L of H. And once you have this, you plug in A and plug in B, and this gives you that this is a bounded set of operators. So FAB of TL, 0 less than A less than B, is a bounded set of operators in the linear operators. And once you have that, we are done. Using this 2 epsilon argument here, everything is okay. Okay. So that's the Calderon reproducing formula. And I said we will use this again and again in this course. And yeah, it looks a little bit innocent, and it's always the problem if you write down such a proposition that states you can write some tiny little nice u with a more complicated formula. The question is, why should one be interested in writing the small little u with a more complicated formula? And the answer is because it gives you the possibility to bring into a proof nice things that you know about your functional calculus. And so I would say some words about typical application of this Calderon reproducing formula is like that. So you have some function, some regularly decaying function g that is non-zero, because otherwise you cannot apply Calderon formula because you cannot normalize to 1. So this is a given thing, and this is a nice function in the sense that you know something nice about this operator g of TL. Somehow you know these operators behave nice in some way, and you want to use this in some proof. What you then usually do is you pick some other function, some other nicely regularly decaying function h that somehow normalizes your g, so that integral of 0 to infinity g of t h of t dt over t is 1, so that you can then apply the Calderon reproducing formula to g times h, because this has the right normalization behavior. You could now say, okay, why not just normalizing g? for instance, it could be that your function g gives a zero integral here. So that this integral is zero, then you cannot just normalize by a constant, but perhaps you can normalize by some h. And secondly, sometimes it's interesting to have another function h here at your disposal. The other question is, where on earth should I get such an h from? Does this exist always? Does it exist? Is there an instance where it exists? Why should it exist? And one answer is, so one example how you can always construct such a function h is just take h of z to be constant, some constant to the -1, the holomorphic conjugate of g of z, where the c has to be chosen as integral from 0 to infinity g of t in modulus squared dt over t. And note this is always a finite number. Now, because this has polynomial decay at 0 and infinity, and so this is okay. And note, this is always a finite number, and also this is always a strictly positive number, because the f is, the g is non-zero. This is a sort of 2 norm, so this is strictly positive, and so you can invert. And yeah, this is the holomorphic conjugate, which also always exists. And if you take this as h, you will find that here you have 1, because g of t, h of t is g of, for real arguments, the holomorphic conjugate is just the complex conjugate. So then you have g times the complex conjugate of g. This gives you a norm of g squared, modulus of g squared, and the c is exactly what makes this to 1. So such a function always exists, even if you are unlucky and this integral is 0, and you cannot just normalize by a constant. You will always find a function h that gives you this function being 1. This value of this integral being 1. So, and once you have this function h, you apply 616, so the Calderon reproducing formula for the function f being g times h, because this has the right normalization features. And this gives you the formula that u can be written as an improper integral from 0 to infinity h of tl, g of tl, u dt over t for all u in the closure of the range of L, or if you know that your operator is injective, for all u in H. And now in this formula you can use any nice features that you know about your operator g of TL and get something interesting for you. So that's the general way how this theorem is used. And you see, whenever you have some g that is non-zero, you need such a function h that makes it run. And this function h, so this auxiliary function that gives you the right normalization will now get a name. So that's the next definition. Take the right angle phi. Take some function g, as we had here, regularly decaying. And any function h that is also regularly decaying that does the right normalization, so such that the integral of 0 to infinity g of t, h of t, integrated with respect to Haar measure gives you exactly 1. We've seen such a function h always exists if g is non-zero. If g is 0, this cannot work. But as soon as g is a non-zero function, such a function always exists. And such a function will be in the following called a Calderon sibling of g. So this is just introducing some words just as that you can write shortly, let g be and let h be a Calderon sibling of g, and meaning that h is chosen the right way to make this work. Okay. And I want to show one concrete application of this Calderon reproducing formula that also gives us new insight on the square root of L, of our sectorial operator. And this is a formula that goes back to Balakrishnan, and it's usually called Balakrishnan representation of the square root. You can prove this by other means. So what I will show you is a proof by functional calculus. When Balakrishnan did this, I think someone in the 60s or something like, or 50s, it's rather old, there was no functional calculus around. He did it in a different way, but you can use the Calderon reproducing formula in a rather elegant way to prove this representation. So, and what does this tell you? So this gives you a formula to calculate fractional powers. So fractional powers for real part of alpha between 0 and 1. But if you want to do with L to the 3/2, you just take L times L to 1/2. So then this is the interesting range. So you want to have a formula for these exponents. And then I claim that for every u in the domain of L to the alpha, you can calculate L to the alpha u by taking sine of alpha pi divided by pi. This is just a normalizing constant. Do not worry too much about it. The interesting part is the following integral: 0 to infinity t to the alpha minus 1 L t plus L to the minus 1 u dt. Interesting thing to do, just to get a grip on that this somehow is a formula that might hold. Put in numbers here, so put in an a here, or some number a, yeah, and calculate this integral in the reals, and you will find this is a to the alpha. So should work, yeah? And what Balakrishnan says, it works. Okay, and how do we prove this? I will show you the proof if L is injective. Then it's a little bit easier, and if it's not injective, because if L is injective, you can apply Calderon's reproducing formula for every u in H, and you do not have to bother about the range of L. But there's a way around. So if we have enough time, I can tell you how to get around. But let's do the important part of the interesting part of the proof to show that for injective L. So the core of the proof is to show that for injective L, you have this representation, representation of the fractional power. So take some u in the domain of L to the alpha. And then what we need is the following identity of integrals. So integral from 0 to infinity, tau to the 1 minus alpha over 1 plus tau d tau over tau. For some people, this is a known integral. Perhaps one has, sometimes it appears in a complex analysis class, but it need not. But this is, what you need is, and just look it up in some tables or in the internet, this is pi over sine of alpha pi. As I said, this will give you this constant. This constant is of no further importance for the rest of the lecture. You could just put a constant here, but this is the right value. Yeah? Okay, we need this one. And once we know this, we know that the function f that is given by the inverse of this constant, so sine of alpha pi over pi, times z to the minus 1 is alpha, 1 plus z to the minus 1. This is a function with a regularly decaying function. In 0, there is some decay here. Minus 1 is more than 1 minus alpha, so there's some polynomial decay at infinity left. So this is a H0 infinity function. So we can plug in L, and we want to use the Calderon reproducing formula So that's why we have this prefactor, and this prefactor tells us that the integral 0 to infinity f of tau d tau over tau. This is exactly this integral. This is pi over sine times this is 1. That's why I have this prefactor. Okay. So we can apply the Calderon reproducing formula 616 to this function f, and it gives us that L to the alpha u, this I can do because u is in the domain of this operator, and I will now apply this is an element of our Hilbert space H. I have an injective L, so the formula is valid for all elements of H, so I can take this one. And this gives us the integral from 0 to infinity f of TL L to the alpha u dt over t. So this is the Calderon reproducing formula for this function f and for the element L to the alpha u. Now put in the f, or see another way. So this is a product of two functions coming from functional calculus. The right one is unbounded, so I have to imply 515 and not 59. It's not the elementary calculus, it's the extended calculus. It's even the bad way round, so I have an inclusion of this one into the product of L, but I know that U is in the right domain, so this gives me integral 0 to infinity, integral 0 to infinity, the prefactor sine of alpha pi over pi, integral 0 to infinity, and then there is now put in the L into the F. This gives you this gives you f of TL L no. I'm confused because on my paper it's with a tau, so let's write it with a tau. So this is 515. This is sine of alpha pi divided by pi, integral 0 to infinity, and I'll put in the f at tau L. This gives you tau L to the 1 minus alpha, 1 plus tau L to the minus 1, then L to the alpha u, dt d tau over tau. Okay, now you can have an L to the alpha here, you have an L to the 1 minus alpha here. We know how to, and these commute. Yeah. So we know how to compose these operators, these fractional powers. So this gives you sine of alpha pi divided by pi, integral 0 to infinity, tau to the 1 minus alpha. Then you just have L, L to the 1 minus alpha plus alpha, 1 plus tau L to the minus 1, u d tau over tau. Okay. So this was, if you want, this was 6.3, so the composition rule for fractional powers. Now you do a change of variables, t equals 1 over tau. Why do I do this? Because this can be rewritten as 1 over tau times 1 over tau plus L to the minus 1. And I want to replace 1 over tau by t. So this gives me sine of alpha pi over pi. The integral is still from 0 to infinity. This gives a t to the alpha minus 1. The L is an L. This gives a t times t plus L to the minus 1. And it's again Haar measures, so this is dt over t. So this t cancels out. And what remains is sine of alpha pi divided by pi, 0 to infinity, t alpha minus 1, L t plus L to the minus 1 dt. And let's hope t to the alpha minus 1, L t plus L minus 1, and the u has someone gone astray. Okay, here. Okay, it's the same. So we get this formula by applying this Calderon reproducing formula to this element L to the alpha u, and then the rest is some algebra, some looking closely at the integrals. And now what we are still missing is what happens if L is not injective. Then you get this equality on the closure of the range. And then again you use the decomposition of our Hilbert space H into the kernel and the closure of the range. So you know it works perfectly on the closure of the range, so you only have to look what happens on the kernel. But on the kernel, this formula somehow holds trivially. This formula somehow holds trivially because what you have to think about is that if u is in the kernel of L, then it's in the kernel of L to the alpha. But this we had at some point. So then you have 0 here. And on the other side, if u is in the kernel, it's in the domain. So you can take the L over here, and then you get 0 also on the right-hand side. So on the kernel, it's 0 equals 0. Yeah? And this means you can put it together and have it on all of the space. That's the idea. In the lecture note, the argument is given. But I'm short of time, so thank you very much for listening. And see you again next week.